In this video lesson, we're going to do an introduction to equilibrium calculations. So what we're really doing is looking at two fairly straightforward types of calculations that we're going to be using a little bit more frequently as we look at reactions in equilibrium. From this point forward in the video, you're going to want a copy of this handout that you can get from your teacher or from our site on equilibrium calculations. So the first type of reaction that we're going to look at is percent reaction. What we know about equilibrium is that the concentrations are going to stay the same for a system regardless of if the equilibrium is reached from the forward direction, so starting with what we traditionally call reactants and making our products, so going from left to right of the equation, or if we go from products to our reactants, so we go from right to left on our balanced chemical equation. It doesn't matter which direction we approach equilibrium from, but we always get to exactly the same concentrations of our reactants and our products at equilibrium. So in order to communicate how far a reaction proceeds before it reaches equilibrium, we calculate something called percent reaction. The percent reaction is really how much product we have at equilibrium, and we get this percent reaction by calculating it. So our percent reaction is calculated by really just calculating percent of anything. So actual product yield divided by theoretical product yield times 100%. And so our theoretical product yield is really the max amount of product that we can get if the reaction went 100% to completion. The number we get when we calculate percent reaction can tell us a lot about what's happening. So I want you to find a place on your page to write this in here, because basically if our percent reaction is less than 1%, we really say no reaction happens. If it's less than 50%, we say that the reactants are favored, so there's more reactants than products. If it's greater than 50%, we say the products are favored, so we've made more product than we have of reactants. And if it's greater than 99%, we say that the reaction is complete. This is our first type of calculation for equilibrium, just looking at percent reaction, so nice and easy and straightforward. The second type of calculation we're going to look at is calculating concentrations at equilibrium. So we wanted to be able to determine how much of each reactant and product we have when the system has reached equilibrium. And to do this, we use something called an ICE table. So in an ICE table, we have an I, we have a C, and we have an E. So when we're using these ICE tables, our I stands for concentration of reactants when we start, so initial concentration. The C represents the change in concentration between start of reaction and equilibrium, and our E represents the concentrations of reactants and products when we're at equilibrium. So we're going to jump right into an example here. In our example, we have a concentration of 1.00 mole per liter of hydrogen gas and fluorine gas, and they're combined in a closed system, and I think this should say 2 form, hydrofluoric acid, HF. We want to know what the concentrations of the hydrogen gas and the hydrofluoric acid at equilibrium if the equilibrium concentration of F2 is 0.24 mole per liter. So the very first thing we need to do when we start these things off is start with our balanced chemical equation. So our balanced chemical equation, we are starting with hydrogen gas and fluorine gas, and we're making hydrofluoric acid. So this is what our reaction looks like, and if we take a quick look, we notice really quickly that it's not balanced. So to balance that up, pretty straightforward, we just need to put a 2 here. Then we're going to start our ICE table. So remembering that our ICE table has an I, a C and an E. I represents initial concentration. So we know our initial concentrations of both the hydrogen gas and the fluorine gas are 1.0 mole per liter and 0.0 mole per liter. And we know we're starting with 0 mole per liter of the hydrofluoric acid. Okay, I'm just going to zoom in a little bit to make it a little bit easier for me to write in all the information. The next part of our ICE table is C, our change in concentration from the beginning to when equilibrium is reached. And what we do is we use an X to denote that. So we say that our change is going to be an X here, and an X here, and an X here. Now, when we're looking at our reactants, we know we're going to lose reactants. So that means that we're actually going to have a negative X for our reactants. So if you need to, you can make yourself a little note and say this is negative because we lose reactant. When we're looking at our product, though, it's going to stay as a positive because we're going to gain our products. The other thing we have to remember is that according to our balanced chemical equation, we have an invisible one here and an invisible one here and a 2 here. So what that means is that we're actually going to have a change in our X for our product is going to be a 2X. Once we figure out what change is going to happen, we can then pretty easily establish what our concentrations are going to be at equilibrium. So our initial concentration was 1.00 and for 1.00 mole per liter for hydrogen gas, and we have a change by subtracting X. The exact same change is going to happen for the fluorine gas. We started with 1.00 mole per liter. We are going to have a change of negative X. So our equilibrium is going to be 1.00 mole per liter subtract X. And then our concentration of our product for our hydrofluoric acid is going to be our initial, so 0 plus 2X. Once we know what kind of changes we're going to see happen when our reaction has met equilibrium, we can solve for X. To do this is quite straightforward because we have the information that we need to solve for X. In our word problem, it tells us that the equilibrium concentration of fluorine gas is 0.24 mole per liter, and we down here just said the equilibrium concentration of fluorine gas is 1.00 subtract X. So we just solve for X. I'm just going to zoom over here to make that happen so I have a little bit of space. So basically what we can do is we can say concentration of fluorine gas equals 1.00 subtract X, and we know that's going to equal 0.24, and we should include our mole per unit. So therefore we can say that 1.00 subtract X is going to equal 0.24 mole per liter, and that's pretty easy to solve for. We subtract 1.00 from each side, 0.24 mole per liter subtract 1.00 mole per liter. We end up with a negative number. Negative X is going to be negative 0.76 mole per liter, and then you just multiply both sides by negative to get rid of that. X equals 0.76 mole per liter. So that is our concentration of fluorine gas at equilibrium. now that we know what X equals, we can use that to solve for our concentration of hydrogen gas. Because we know that the concentration of hydrogen gas is going to equal 1.00 subtract X. We know X equals 0.76. So therefore we know, we do that math, that the hydrogen gas concentration is 0.266 mole per liter. We can do exactly the same thing to solve for the equilibrium concentration of hydrofluoric acid. But this time we know that it is going to be 2x, so we go 2 times 0.76, and we get 1.52 mole per liter. So what we know is that our concentrations of our fluorine gas is, well, we knew that already, is 0.24 mole per liter at equilibrium. The hydrogen gas concentration at equilibrium is 0.26 mole per liter, and the hydrofluoric acid concentration is 1.52 mole per liter. So you should finish that up with a therefore statement. So there's our therefore statement there. So make sure you have this whole example copy down here before you continue on into the video to look at yet another example of using these ice tables. We're going to go through the next example a little more quickly. I'm not going to show you as much of the work, but you'll pick it up pretty quick. So in this second example, we have 4 moles of NH3 being added to a 2-liter container, and it gets heated up so it decomposes into nitrogen gas and hydrogen gas. We know at equilibrium there's 2 moles of NH3 in the container, and we want to know what our concentration of our hydrogen gas and our nitrogen gas is going to be when we reach equilibrium. So this example is a little bit different because we're not given our concentrations. Instead, we are given the moles of NH3, initially, and the moles of NH3 at equilibrium. And we know we have a volume of 2 liters in that container. So we have to use this information first thing to calculate our concentrations. We need to convert this mole and this volume data into concentrations for the NH3 initial and at equilibrium. So the math looks like that. You should know how to calculate concentration from mole and volume, but if you don't, you can see exactly how I did it here. Our next step then is to get our balanced chemical equation and set up our ice table. So here's our reaction. A quick look at our equation, and we can see that we're not balanced, and to balance that, what we have to do is put a 3 here and a 2 here. And the other thing I want to point out to you is that now we're dealing with equilibrium reactions. We don't write our arrow to look like this anymore. What we want to do is we erase this and we write an arrow on the top, doing this, showing it can go forward, and a half arrow on the bottom showing it can be reversed. So if we did not do that in the last example, go back and fix that. Now we start putting in our data into our ice table. We know our initial concentration of our NH3. We calculated that right here. So here it comes down here, 2.0 mole per liter. And we know that we start with 0 hydrogen gas and 0 nitrogen gas. Our concentration or our change from equilibrium, from initial to equilibrium, again, we represent as an X. So we put an X here, an X here, and an X here. And then we have to manipulate that X. So for our NH3, we know because there's a 2 up there, we need to put a 2 here. And because it is a reactant and we're losing reactants, we say it's going to be a negative. We're going to see a decrease in amount of reactant. Our hydrogen, because we have a 3 up here, we have to put a 3 here, and we're gaining product, so we put a plus in front of that. And then our nitrogen, we have an invisible 1 here, so we can just leave it, and we do write in our plus to show that we're gaining. So then it's pretty straightforward. Our equilibrium concentration from our NH3 is going to be 2.0 subtract 2x. Our hydrogen concentration is, we're going to have 3 times whatever x was, and our nitrogen gas concentration is going to be just an x. So once we have this set up, we need to solve for our x. And again, you need to have some kind of given information. And so if we go back and we look, we know that our equilibrium concentration of NH3 is 1.0 mole per liter. And so we know that 1.0 mole per liter is going to equal 2.0 subtract 2x. So we can set it up to look like this, and then we just have to rearrange to solve for our x. So we're going to know 2.0 subtract 2x is going to equal 1.0 mole per liter. And we just start rearranging 2x. Remember that negative is in front of that x, is going to be 1.0 subtract 2.0. Just going to move my paper up a little bit. And so on and so on. So we do all the math and we get x is going to equal 0.5 mole per liter. So now we're going to take that number and sub it back in for our concentrations for nitrogen gas and hydrogen gas. And I'm going to do that just up here on your page, but you probably haven't written as big as me, so you probably have space to do it below. So for our concentration of hydrogen gas, we know that at equilibrium, the concentration of hydrogen gas equals 3x. So we just go, concentration is going to equal 3x. It's going to equal 3 times 0.5. So our concentration is going to be 1.5 mole per liter. Then we're going to do exactly the same thing for the nitrogen gas. Over here in the ice table, it tells us that it's just going to be x, so that one's really easy. N2 concentration equals x, so therefore it equals 0.5. I'm just going to write my units underneath, mole per liter. And then you just need to write a therefore statement again. So there's our therefore statement. Therefore, the concentration of N2 and H2 are 0.5 mole per liter and 1.5 mole per liter respectively. So just because this note's kind of all over, so just because this note's a little bit all over the place, I'm just going to number your steps. So your first step is you need to calculate the concentrations. The second step is a balanced chemical equation. And then third is your ice table. The fourth step was to solve for x. And then your fifth step was to get the concentrations of what the question was asking you for. So if you're feeling brave with this, go ahead and try some of this practice. You should be able to do them. It's pretty straightforward. We will do some more in class together another day. Good luck with that practice.